We have studied objects moving along straight line paths, such as in the x-axis. Now we look at objects that move in both the x and the y directions simultaneously. Because position, velocity and acceleration in 2D can have two components, x and y, we need to use quantities that reflect this. We will use vectors to represent the direction and magnitude of these variables, position, velocity and acceleration. An important special case of two-dimensional motion is called projectile or parabolic motion. Anyone who has tossed any kind of object into the air has observed projectile motion. If the effects of air resistance and the rotation of Earth are neglected, the path of a projectile in Earth's gravity is curved in the same shape as a parabola. So we have something like the positive x direction is horizontal and to the right plus x, and vertical and up is positive y. The most important experimental fact about projectile motion in two dimensions is that the horizontal and the vertical motions are completely independent of each other. This means that motion in one direction has no effect on the motion in the other direction. If a baseball is tossed in a parabolic path, the motion in the y direction will look just like a ball tossed straight up under the influence of gravity. In general, the equations of constant acceleration developed in previous lectures follow separately for both the x-axis and the y-axis. An important difference is that the initial velocity now has two components, not just one. If theta is the angle between the vector and the x-axis, then we have that Vx is going to be V times the cosine of theta, and Vy is going to be V times the sine of theta. Now let's assume this projectile motion where we have an initial velocity of V0, V0x, V0y for the two components. We have a motion with constant acceleration in the y-axis and with constant velocity in the x-axis. Therefore, the equations that describe this projectile motion are, in the x-axis, this is going to be x0 plus v0xt, and in the y-axis it's going to be y is equal to y0 plus v0yt plus 1/2 of at squared. Well, remember that the acceleration is minus 9.8 meters per second squared if you are at the surface of the Earth. At any instant in time, the velocity is going to be the square root of vx squared plus vy squared, where here in this type of parabolic motion, projectile motion, vx is going to be constant. So this is v0x, this is v0x, this is v0x. So this will always be v0x, and this vy is going to be changing. Maximum down here is decreasing until it reaches the maximum height, and then it's going to be decreasing. Sorry, it's going to be decreasing but increasing in magnitude, and I mean decreasing because it's going to be negative because it's pointing downwards. The angle, this angle here, we can always calculate it with trigonometry. We know that the tangent of theta is always going to be this divided by this, so it's going to be vy divided by vx. Let's solve a problem on parabolic motion. A rescue plane drops a package of emergency rations to a stranded hiker. The plane is traveling horizontally at 40 meters per second at a height of 100 meters above the ground. Where does the package strike the ground relative to the point at which it was released? What are the horizontal and vertical components of the velocity of the package just before it hits the ground? So what we have here is that initially it's traveling horizontally, and because of the action of gravity, we have this is going to be the trajectory, and it's going to hit the ground. So initially we said that this is x equal to 0, and this is the y-axis, and initial height is going to be 100 meters, initial x position is going to be 0. So we know that initial velocity is only in the x-axis. So the package has exactly the same velocity as the plane, and that is 40 meters per second. And we know that because there is no acceleration in the x-axis, that's going to be constant velocity. We have the acceleration in the y-axis is negative 9.8 meters per second square. So first, let's write equations of motion that we have for this type of motion. We know that on the x-axis, this is x0 plus v0x time, and in the y-axis, it's y0 plus v0yt. Okay, so let's write the initial conditions and rewrite this. X is equal to just 40t, and y is equal to 100 minus 1/2 of 9.8 t squared, because the initial velocity of y is 0. So now we want to calculate what is going to hit here. So we just solve this system of equations, and then we find the time to reach that point and the x position. What's the condition of hitting the ground? Well, the condition is that y has to be 0. So we impose y equal to 0 here, we find time, and once we have time, we find the distance. So let's say this and then we have that 10 times 2 divided by 9.8 is equal to t squared. So we have that time is equal to 4.52 seconds. That's the time that the packet needs to hit the ground. Now that we have this result, we substitute here and we get the position, the x distance, the horizontal distance traveled. So x is going to be 40 times 4.52, and this is 181 meters. So that's the horizontal distance traveled. Now we want to know what are the components of the velocity right here. We know that the horizontal is always going to be the same one, but the vertical one here was 0, but it's increasing. So if we just draw the vector velocity here, this is going to be Vx, which is going to be V0x. And now here we're going to have a Vy component, which is going to be different from 0. Let's calculate that. To calculate the final velocity in the y-axis, we get this expression. And from here we have that Vy is negative 9.8 t, and this is 9.8 4.52 gives negative 44.3 meters per second. That's the velocity in the y-axis. If we want to calculate the magnitude of the total velocity, it's just the square root of Vx squared plus Vy squared. And I let you to do this.